Thank you, everyone, again. So this is actually about the new capabilities at the Wall of Wind. That is ongoing effort and future capabilities. It's two different topics. It's not related. Hybrid simulation is one topic. The other one is downburst simulation. So I will start with the downburst simulation at the Wall of Wind. So far, Wall of Wind is capable for simulating the synoptic and straight winds, hurricane winds. Downburst is another extreme wind event. It's basically a vertical wind that descends to the ground from the cloud, impinge on the ground, and create a devastating wind intensity very close to the ground, which is the typical heights of our civil infrastructure. They can be classified with respect to the size, very small, less than 2.5 miles, or a large macroburst is greater than 2.5 miles. But they have similar characteristics. You can tell from the footprint of the damage, a straight wind kind of damage could be related to downburst, a thunderstorm. And this is why sometimes we confuse a straight wind with a thunderstorm downburst. On the other side, a tornado is more like a circular kind of damage. Why it's important to study downburst? It is very different to synoptic wind. The characteristics, starting from the window profile, the ABL window profile is smaller near the ground, while the downburst has the highest or the maximum wind speed near the ground. And this is why it's devastating on the structures. It's obvious here. Most of our codes are just considering the ABL. More importantly, a downburst has two components, a radial or horizontal velocity and axial or vertical velocity. It also has a rotating rolling vortex. And with respect to the time history, downburst is very dynamic. Temporal non-stationarity here is obvious because you can see a dramatic change of this ramp up and ramp down, increase and decrease in the wind speed. Those are four different time histories for four different events. I was talking about the rolling vortex. You can see here from this field photo, the rolling vortex is affecting the large span of a transmission line system. It's very localized in space, as you can see, in addition to the temporal and the time localization. Again, the challenges is the lack of design guidelines. Wind profiles and time histories are completely different compared to synoptic winds, and the localized nature. And the localized nature means that it's difficult to measure and forecast in field, and it is not non-uniform. It's very localized here on the span. So this causes unique wind loading scenarios especially on long span structures, as you can see from this schematic. It's evidence that downbursts are devastating. You can see it in different infrastructure. I'm not going to stop here. To simulate that in a wind tunnel setting, we have to consider not just the time and the velocity or the intensity, but also the geometric parameters of the downburst. In terms of the diameter of the cloud, all right, and the height where this cloud starts to the ground, and also the point of interest, where the structure of interest is located compared to the center or from the center of this event. Okay, so we have some parameters that we need to consider in the analysis. We received an NSF funding to assess the feasibility of simulating downburst in the Wall of Wind, the NHERI Wall of Wind. We started with this small scale tool. Is very, very nice. A small scale Wall of Wind is very nice tool because it enables us to do more testing at a very low cost. So study different ideas. This is completed, and we are about to send the first paper for that very soon. In this experiments, we utilized two different downburst simulator techniques. One is called the impinging jet, where we simulate the cloud, falling down to the ground. And the other one is the wall jet, where we use just the straight wind, and by means of blockage and gate or slat louver opening and closing mechanism, we can create the rolling vortex and the high intensity wind near the ground. So we tested different designs to see which is the best, and the best means, well, okay. Sorry, let me go back one step. The best is, from our perspective, is that we are able to simulate downburst at a good scale, because we want to utilize, you know, the big advantage of the Wolf wind, which is larger scale testing. This is one of the simulators that we thought is the most feasible and practical, because it only has like two slats. And from here, you can see from this flow visualization, you can see the formation of the rolling vortex. And we did also some preliminary analysis using CFD simulation to see the propagation of this vortex, the rolling vortex, and the motion along the test section at the wall of wind. With respect to the flow characterization, downburst flow characterization, again, is another challenging part. As you can see from a total time history of the event, the mean wind speed is different, is varying, which means that the dynamic response of the structure is affected by the mean, not just the fluctuation part of the time history. It is challenging because we need to do like a trial and error kind of process to estimate the averaging time or the moving mean window that we use. So it's not like just a 3-minute or 3-second gust or 1 hour kind of mean. No, it's a trial and error. We were able to validate actually all the simulators that we tested. So all of them were successful. It's just which one is the most practical. As you can see, the characteristic nose shape of the profile is obtained, where the maximum wind speed is happening near the ground. We believe that the simulator is flexible because we can do different scaling ratios, very small, like 1 to 2,000, to quite large, very large one, almost 1 to 10. Scaling is challenging here because it's not just the geometric scale with respect to the height of the peak, but also the time scaling for the peak duration, the acceleration of the event at the ramp up, and the deceleration at the ramp down. So it's two different scaling ratios. We try to come up with an understanding of what the simulator can provide. Currently, we have 2 NSF projects funded or actually utilizing this simulator. One is to assess or to characterize the fragility of transmission line systems under downburst. And the other one is structural response in transient winds of hurricane and downburst. That's Dr. Tengu at the University at Buffalo. Okay, I'm running out of time, but the second part of the presentation is the hybrid simulation capabilities and research opportunities. This is a new cross-award activities that we do with the Lehigh NHERI facility. Currently, the capabilities of any wind tunnel testing is that, or in wind engineering, is basically conducting like wind tunnel testing to obtain response pressures, or do numerical simulation using CFD, and then from structural perspective, do the finite element modeling, use the wind pressures from wind tunnel or CFD simulations. These are the current state of the art. Hybrid simulation can combine finite element modeling together with wind tunnel or CFD simulations to make use of to make a better use of the capabilities of both the wind tunnel and finite element modeling. The advantages of real-time hybrid simulation or hybrid simulation in wind engineering is that if you substructure your model, then you can do larger scale. And this would eliminate scaling effects. And I will discuss the scaling effects in a minute. Also, more importantly, in wind tunnel testing, we are not able to simulate the nonlinearity effect. Okay, so if we couple both wind tunnel and numerical modeling, we can capture the nonlinear effects as well from the numerical setting. If we go larger, we can better understand the wind-induced response, the aerodynamic damping effect. Recently, we're talking all the time about multi-hazards and multi-physics fluids. So allowing the real-time hypersimulation in a wind tunnel testing means that we can combine wind and wave, for example, or wind and flooding. So this is, in our opinion, these are the main advantages of utilizing or bringing the real-time hypersimulation technologies, not just from the earthquake field to the wind engineering field. I was talking about the scaling effect. So this is just a brief example of like why it's important to go larger scale, okay? Here, the full scale wind speed is, let's assume it's a 50 meter per second, and the diameter of a cylinder that we are studying is 2 meters. Then the Reynolds number is the order of 10 to the power 6. So the drag coefficient, which represents the force on this cylinder, is at this point, this red line here. If we go like a typical length scale of 1 to 500 and the velocity scale of 1 to 10 and test that at the wall of wind or at the wind tunnel, then our Reynolds number is much smaller. Your drag coefficient is completely different. And this was proven actually from this Burj Khalifa testing at RWDI. So they did the entire tower at 1 to 500, and then they took the top portion and tested at 1 to 50 instead of 1 to 500. So it's much, much larger. The discrepancies of the base reaction were in the order of 20–25%. So this highlights the need for larger scale testing. The problem is that also in small scale testing, if we have a time scale of 1 to 60 using the same kind of ratios of length scale and velocity scale, we obtain a time scale of in the order of 1 to 60. It means that your 1 second in the wind tunnel represents 1 minute at full scale. And more importantly, 60 hertz in wind tunnel represents 1 hertz of your model, like at full scale. So this means that in turn, you need a very fast numerical simulation. You need, your actuation may not be able to apply deflections at adequate frequency response. While by changing these scaling ratios, instead of 1 to 300, go 1 to 20, or and using the same velocity scale, so the time scale is extremely larger, 1 to 4 instead of 1 to 60. This is a big change here in the time scaling, where the 1 second in wind tunnel is only 4 seconds at full scale, so it's much closer, and 4 hertz of the frequency is 1 hertz at full scale. So it's very close to the full scale wind structure interaction. So in turns, we can do like more numerical simulation. Okay, I'll try to run this. This is the tower and the telecommunication tower project that we are doing at the Wall of Wind in collaboration with Lehigh. So far, we did already the aerodynamic testing. We collected pressure measurements on the tower, or the building and the tower. We transferred those pressure measurements to the numerical model at Lehigh. They are doing 3D finite element simulations to get like a baseline of the problem, so we can understand what is expected in testing when it comes to testing. The setup that we envision is basically, we have the tower connected at the base with actuations. The actuation is informed by the building behavior simulated in the computers. We run the fans, and then simultaneously in real time, using a very small time step of 1/1000. We assess the aeroelastic response of this very important infrastructure tower to assess their functionality in events of wind events. Major challenging is or a research question that we need to answer in this project is the forcing function. If we collect the forcing function in one experiment and then use it for another experiment, how is this reliable? The definition of the forcing function is used in the numerical simulation. And I can discuss that just because we're running out of time quite late. I can discuss that later if you have questions. I know that we have a wide spectrum of researcher interests here in this workshop meeting. So these are possible like hybrid simulation application and wind testing, you can think of it. Transmission tower systems, you can simulate conductors as a substructure in the wind tunnel. Cladding problem and water penetration, you can get like a cladding panel in the wind testing setup and then do wind-driven rain, like what Johannes was discussing. While the actuation is, simulating the displacement of the structure, the building. Offshore structures like wind turbines, you can do, as I said, multi-hazard wave actions using the actuations. Damping systems on tall buildings or communication infrastructure. So many buildings actually can benefit from this technologies in wind tunnel testing. The important announcement that I want to make here is that recently, in collaboration with the MIX Coordination Network under the leadership of Dr. Shirley Dyke at Purdue University, we established a committee on real-time hybrid simulation and fluid structure interaction. This committee brings together researchers from different institutions, United States, Canada, Denmark, Norway, Colombia, and they are from different fields, real-time hybrid simulations, wind engineering, and wave engineering. And we try to leverage the technology, the current technologies, to include fluid structure interaction applications to foster the capabilities and wind and wave testing methods. I'm chairing this committee, so if you have any question about the committee or if you want to collaborate, send me an email. I'll be happy to discuss that with you. And I'll be very happy to include your ideas and projects in our reports. So I think that's it from my side. Thank you very much for listening. So sorry for the late. And I'll be happy to answer questions if there's any.
Yes, Amal, it looks like there is a question about if there are other collaborations around hybrid simulation or if it's exclusively with Lehigh.
No, actually, it's open for all. It's just we are trying to prove the concept currently with Lehigh, but it's with everyone. Like.
Anything other than that, there were some requests for videos that I think we can take care of through the chat. I'll just ask one more time if there's any other questions. We'll pause for a moment to see if the chat activates. And if not, it looks like we are safe to transition over to our colleagues at the SimCenter.
Okay, perfect. Thank you.